Hello class, this is Dr. Anderson, and let's continue talking about pulmonary physiology, and we're going to concentrate on compliance, surface tension, and airway resistance. So here are our learning objectives. We want to talk about what compliance is and how you measure it, why compliance would increase or decrease, and what are the things that contribute to compliance. So we want to talk about those. Before we get into measurement of compliance, we're going to talk about surface tension. What is it? How does it influence breathing? How is it influenced by surfactant? How does surfactant help us with the law of Laplace? And what happens if you don't have surfactant? And then we're going to talk about airway resistance, and the big thing here is going to be radius. And then we're going to finish up with a clinical application of how compliance and resistance influence pediatric function. So as promised, the first thing we need to talk about is the concept of surface tension and surfactant and all those sorts of things. So this is a device that measures surface tension, and that's not what's so important about this diagram. I really like the legend here. So this is a device that's used to measure surface tension. Surface tension is something that happens at the air-liquid interface. So in this particular experiment, they have just water in the device, and they move the device back and forth, and you see what the surface tension is. Then they can add detergent to the bath, and then as you move as the device is moved, that detergent then lowers the surface tension, and you see a decreased measurement on the gauge there. So the addition of the detergent reduces the surface tension. And then they could also do experiments where they could lavage the lungs, get some surfactant from the lungs, and repeat this experiment. So, interesting thing, water alone, the surface area doesn't matter. The water interface is the same everywhere. There's no difference. If you add detergent, surface tension is the same everywhere, doesn't matter what the area is. However, there's something special about surfactant, that the property of surfactant and the surface tension changes with surface area. Hold on to that, because we're going to get back to that. Now, this big fluffy cell right here is a type 2 alveolar cell. Notice it's got all kinds of mitochondria and little organelles in here, because these are little surfactant factories. So we have the type 1 cells that are the diffusion barrier. So you see this flat cell here, the diffusion barrier. But then we have other cells that produce the lung surfactant. Surfactant is an amphipathic molecule. So it's got phospholipids and other kinds of substances in it. So notice what's going on here in this little circle, and you blow it up. So this looks very much like a phospholipid. Well, this particular is a phospholipid. So we have two fatty acid tails, and those are lipid-loving. We have a glycerol base, and then we have a phosphate and a choline. So this is polar. So when you have a molecule that's nonpolar and polar, both of those characteristics, those things are called amphipathic. Now notice what's happening here. So surface tension occurs at a liquid-gas interface. The polar part inserts itself into the liquid, whereas the nonpolar part sticks out into the air. Now, what does that do? That breaks up hydrogen bonding that can occur in the water. So remember hydrogen bonding? So here's a water molecule, and it could form a little association with another water molecule. And so droplets of water like to form beads, But when with this surfactant substance on the top of the water spreads out in a film. So surfactant lowers surface tension, but there's something about surfactant that enables surfactant to have an area-dependent sort of thing. So if you have surfactant in a little alveolus versus a big alveolus, surface tension will be lowered more in the small alveoli. That's because there's this area-dependent aspect of surfactant. The other thing is, as the lung is changing volume, so when you're inhaling and exhaling, as the lung area and the little alveoli get smaller, the surfactant molecules are compressed. And so then you inflate the lungs, and then the surfactant gets spread out. So this not only helps in the function of surfactant, but it helps in the turnover and replacement of surfactant molecules. All right, what does all this have to do with a real lung? What I'm showing here in this diagram is two alveoli with no surfactant. We have one alveolus with radius A and another alveolus with radius B. Radius A is much bigger than radius B. Now, I'm here to tell you, if I had two balloons connected like this, and one balloon had a smaller radius, that balloon would collapse and blow up the bigger one. That suggests that the pressure in the smaller balloon, or the smaller alveolus, is greater than the pressure in the larger alveolus, and that is indeed true. If you do this experiment, this alveolus would collapse and blow up the bigger one. Why does that happen? It happens because of the law of Laplace. What we assume is if these alveoli have no surfactant, then surface tension is the same everywhere. That means the surface tension in alveolus A is equal to the surface tension in alveolus B. And if that is so, then the pressure in alveolus A is smaller than the pressure in alveolus B. Then the air flows from B to A, and the alveoli collapse into one another. You can show this very thing through looking at soap bubbles. So fill up a sink with soap bubbles, and you watch them over a course of the evening. The smaller bubbles will collapse and blow up the bigger ones. And over the course of the evening, the bubbles will become fewer and fewer in number, but larger and larger in size. Now, how's come your alveoli aren't collapsing all over the place? Because there's surfactant. Surfactant helps us defy the law of Laplace. How does it do that? Surfactant is found inside these little alveoli. And remember that the polar parts in the fluid is in the liquid, and then the little tails are sticking out into the air. And they're all around here, lowering the surface tension. By allowing the water to spread out in a film, we don't have the water all beating up and pulling more fluid into the lungs. And because of this area dependence, now in our little diagram it says we have a lower surface tension in alveolus B, so it's lower here than here due to a unique property of surfactant. So we don't really know how surfactant works. We know surfactant disrupts hydrogen bonding between water molecules. It helps the water spread out in a film so it doesn't beat up and cause the alveoli to collapse. But why it has this area-dependent behavior, people are still working on that. What we do know is that when surfactant is present, there are differences in surface tension that are related to area or related to the radius of the alveoli. So surface tension is lower in the smaller alveolus, and that means the pressures are equal. And when the pressures are equal, then the alveoli are stable. So the presence of surfactant stabilizes the alveoli. It also lowers the work of breathing because the lower surface tension means our lungs are more compliant. Now, I want to tell you about a classic experiment, and we'll discuss this in lecture. But in experiments with cannulated animal lungs, so they take lungs out of an animal, put a little cannula in the trachea, and they fill the lungs with air, and they do a pressure volume curve. They put it in a little device, so you have a little jar here, and then you have your little animal lungs in the jar. And then we know the pressure here, and the pressure here, and the pressure here. And you can inflate the lungs and get pressure volume curves. So when you do this experiment, with air, you get a curve that looks like this. There's inhalation, there's exhalation. This difference is called hysteresis. Hysteresis basically is an event that departs from the theoretical. So the best example of hysteresis I've ever heard is you're sitting at a stoplight, and the expectation is that when the light turns green, you step on the gas and you get to go. But that's not actually what happens, because you're maybe the fourth car in line, and the person in front of you is not paying attention, and the person in front of them is putting on their lipstick, and the person in front gets to go first. So the first person goes, then the second person who's putting on her lipstick realizes, oh, it's time to go, and then she goes, and then the next guy who's working on his phone says, oh, it's time to go, and then they go, and then you get to go. So it's not that the light turns green, you step on the gas and you get to go. No, the light turns green and the people in front of you go, and then you get to go. So there's a delayed effect. This is the same thing. We might expect that inhalation and exhalation would produce the same curve, but it does not. However, if you take the lungs and you fill them with saline, you get a better compliance and the hysteresis effect is gone. In other words, you get a curve that kind of looks like this. And the question is, why? And I'll let you think about that. Now, I alluded to a compliance curve, a pressure volume curve. So here we go. Notice our x-axis is transpulmonary pressure, which is alveolar pressure minus interpleural pressure, and our y-axis is lung volume, and we can start from 0, or sometimes it's lung volume above FRC. Now, in green, this is healthy compliance. Notice at very low lung volumes, the compliance has kind of a shallow slope, and then the slope increases. So you have kind of a linear part, and then it levels off again. So this tells us at very low lung volumes, it takes a lot of pressure to increase the lung volume. In the middle, we have nice compliance. At the top, the compliance goes down again. It takes a big pressure change to get a little tiny bit of volume in. That's healthy compliance. Decreased compliance has a much shallower curve. So it takes a lot more of a pressure change to get the air in. This is a decreased compliance. This could be because the lungs are scarred. It could be because the lungs don't have surfactant. It could be because the person has pneumonia or something like that. Now, we have an interesting curve, this blue curve. Notice, with a very small pressure change, there's a huge increase in volume. This is increased compliance. And you might say, well, that's great. If a little compliance is good, then more compliance is better. Well, that's not it at all. This person has emphysema. And what's the problem? Well, the reciprocal of compliance is something called elastance or recoil. Because this compliance is so high, it's very easy to expand these lungs. The problem is it's not very easy to recoil them. So emphysema folks have a problem. Because of smoking or because of a mutation, there's a damage to their lung tissue. And all those elastin and collagen fibers that enable the lungs to expand and recoil have been damaged. It's like a stretched out old sweater. You can stretch it out, but it doesn't recoil. So it's important to be in the middle and have that nice sweet spot so that you can easily expand the lungs and get the air in, but you also want to be able to recoil and get the air out. Now notice if we drew this whole thing, our volume loop would be like this. So notice that in a standardized way, compliance is measured during exhalation. All right, so why would compliance decrease, or why would the lungs get stiffer? Could be because you have congestion of fluid in the lungs, so pneumonia or pulmonary edema. It could be because you're at very high lung volumes. Maybe this person has had long periods of no ventilation or low ventilation because the lungs have collapsed, so a pneumothorax. It could be because of fibrosis. Decreases in compliance cause a kind of disease we call restrictive disease. It's a restrictive pattern, and we'll talk about that more as we get into pathophysiology. Now, what happens if your compliance increases? That happens to most people. If you do epidemiological studies and study why people, what happens to their lungs over time, the tissue in the lung kind of breaks down as we age and lungs get more compliant. An increase in compliance is also seen with emphysema because literally the connective tissue in the lung is being broken down. Now, airway resistance. Airway resistance is influenced by all the same principles that vascular resistance is influenced by. So, Ohm's law and Poiseuille's law. So, airway resistance changes with volume. Why would that be? Well, as you increase the volume, your airways get bigger and the airway resistance goes down. As you exhale and the volume gets smaller, the airways get smaller, and then the resistance goes up. Airway resistance also increases with obstructive disease. So asthma and COPD. So there are two kinds of COPD. We've talked about one already, emphysema. And the other one is chronic bronchitis. Emphysema, because the airway or the lung tissue is being destroyed, the airways are very vulnerable to collapse. And with chronic bronchitis, because of overactivity of the mucus glands, there's a lot of mucus clogs. Asthma is the other thing, and with asthma, the airways, there's constriction of the airways. All of these things are going to decrease the radius of the airways and increase airway resistance, so it makes it harder to move the air through the airways. Now, what about those pediatric issues? Well, the airways of children are shorter, but they're narrower. So they're more prone to obstruction and they have a higher resistance to begin with. Infants up to 8 years have fewer alveoli and thicker membranes, so they have a longer diffusion distance, they have less of a surface area, so that's a problem. Little kids have little rubbery chests. Their chests are very compliant, so they have to work really hard to exhale air, and when they cough, their coughing is less effective. Their respiratory muscles aren't fully developed. They have a high metabolism. They have little hummingbird metabolisms, and they have a high oxygen consumption. And they also have an immature immune system. Another thing we could say is they have this soft tissue. So let's say a kid chokes or has a really bad respiratory infection. You get that soft tissue inflamed, and it swells, and the little airways get very, very small. So you have to be really, really thinking about the problems with airway resistance in little kids. Alrighty, so we've talked about surface tension. Surface tension is the interface between water and air. It makes it harder to breathe with a high surface tension, because that decreases compliance. So surface tension is one of the things that influence compliance. The other thing is you have a sweater in your lungs. You have this connective tissue, collagen and elastin fibers that allow the lungs to stretch and recoil, and when that gets damaged and scarred, the lungs don't expand as well. That's a decrease in compliance. Finally, as we're expanding and collapsing the lungs, the air has to move through the airways. And as the air moves through the airways, it encounters airway resistance. It's important that the airways to be nice and relaxed, that you don't have mucus and things clogging up the airways so that the air can move through. And finally, that children have very rubbery chests. So they have very highly compliant rib cages. That makes it easy for them to inhale, but harder to exhale and harder to make a productive cough. And they have little tiny airways, so they have issues with airway resistance. We have one more topic to go through for our first lecture in physiology. That's the work of breathing. I'll stop it for here, and I know I'll see you back again when we talk about work of breathing.